So, welcome to the presentation of our paper with the name A Precedence-Driven Approach for Concurrent Model Synchronization Scenarios Using Triple Graph Grammars. My name is Lars Fritsche, and this is a joint work together with Jens Kosiol, Adrian Möller, Andy Schürr, and Gabriele Taentzer. So, let me first introduce you to our general scenario. Just imagine that you have two models, M1 and M2, which may not look very much alike. However, they share some information that we want to keep synchronized. And now two users, here we call them modeler 1 and modeler 2, decide to change these models independently from each other so that we can assume that they are no longer consistent with respect to our consistency specification. And naturally, we would expect the changes from one model are to be propagated to the other and vice versa, but this is not always possible because the user's intentions do not always align. Because one user might want to delete information while the other wants to preserve it, and hence we would encounter some sort of conflict. And I want to show you today how to detect those conflicts using triple graph grammars so that we can resolve them and get again consistent models so that we can start the process from anew. And our goal was to find a concurrent synchronization technique that is incremental and delta based so that it has the potential to scale with the size of model changes rather than the size of the model itself, at least for most practical scenarios. And in contrast to some other approaches, we also wanted to be able to detect conflicts deterministically and without altering and touching the models themselves, just by looking at them. And also we wanted that our approach is configurable so that you can implement your own synchronization goals and decide how to resolve conflicts that we have detected for you. And finally, we also implemented and evaluated our approach. So as I said before, we use triple graph grammars in our approach. TGGs are a declarative and rule-based way to define consistency between two models in a constructive manner, where we define how to simultaneously build up consistent models from scratch. In our running example, we have a very simple class diagram model on the left and a documentation model on the right side. And our first TGG rule, CD rule, tells us that we can create a new class together with a corresponding document and a mapping link in between at the same time, and we indicate the creation of elements with the color green. So given that we already have a class with a corresponding document, which is here indicated in black as a precondition, we can use our second rule to create a subclass together with a corresponding subdocument with the ICD rule. And then we can also create methods and entries underneath classes and documents, or even parameters underneath methods that correspond to the documentation entry of the method. Now, given these rules, we can create consistent models. And here we already have a class with a corresponding document, and on the right we see a dependency graph that will depict how these rule applications depend on one another. And each dependency node has basically three components. First, its corresponding rule, which is here the CD rule, and then a box for the source side, which is our class diagram side, and another for the target side, which is our document side. And both boxes are blank since our rule application is still intact. And now let's apply some more rules and enrich our model by creating some subclass and subdocument with methods, parameters, and entries. And as you can see, these changes are directly reflected in our dependency graph, where you also see how these changes depend on one another. However, normally we are not really interested in creating consistent models from scratch, but we would rather like to translate one model into another or even synchronize changes between two formally consistent ones. And TG rules can be operationalized for exactly this purpose, to obtain, for example, forward rules, where the source side is no longer created but expected to already exist, here again indicated in black. And applying this rule would create the missing parts on the opposite sides. Also, if a user deletes all elements on the source side, we know that we have to delete all elements the forward rule has created before to synchronize this. And then we can also, of course, create backward rules in the same way, or even mapping rules, which, given that we already have elements in both models, lets us map these elements together instead of translating them each. Okay, so now armed with this knowledge, I want to show you finally how to detect conflicts. So let's go back to our example from before and let's investigate what happens if a user changes something. So here, he might decide to delete the subdocument together with its entries, which are no longer available. And as you can see, these deletions are being represented on our dependency graph, where the target side has now a removed annotation that tells us that all elements on the target side have actually been removed. And normally, we could simply synchronize this change by also deleting the subclass on, on the class diagram side together with its methods and parameters in order to restore consistency. However, another user also decides to alter the models, but on the class diagram side. What he does is he adds another method which causes a conflict because we cannot translate this method and delete the document. Or we can also not delete the subclass, or we would delete the newly added link between the class and its new method. So hence we encountered what we call a delete preserve conflict. And note that the addition of the method is also represented in our dependency graph, where we see that the source elements have been added anew, but we do not have elements on the target side yet. And what we found out is that we can use our dependency graph to detect this kind of conflict very easily by simply taking the node where elements have been added. Here it's a node that corresponds to the newly added method. And from this node, we traverse over our dependency graph to see whether it depends on the node where the opposite side has been deleted, which is here the deleted document. And doing so, we can easily detect this kind of conflict and give the user the chance to decide which changes he wants to keep and which he wants to drop or revoke. Another kind of conflict that I want to show you is what we call a correspondence preservation conflict, which again can be detected using our dependency graph. However, it requires a slightly different example, which you can see here, where we have three classes with corresponding documents on the other side. And class 2 and document 2 have a corresponding method and entry. And now we apply a simple refactoring and move the class 2 to class 1. And normally we could repair this for you by simply moving the entry from document 2 to document 1. However, another user again might come in and he might decide to move the corresponding entry from document 2 to document 3. Now the problem is that both class 1 and document 3 do not correspond to one another, which is clearly a conflict because we cannot propagate both changes. And we call this conflict correspondence preservation because the only way to keep both changes would be to delete the mapping between the method and the entry so that we would have to translate them both anew. And again, we can detect this in our dependency graph by checking the formerly intact node, which has new annotations that tell us that on both sides, parts have been deleted. And partial deletions tell us that some parts are still present, which we normally would try to preserve for you. The other new nodes tell us that we can retranslate our method and entry, but in contrast to before, these elements are not completely new because we know that the method and entry belong to our formerly intact dependency node. So we can detect these kind of conflicts with our technique and give it to you so that you decide which change you want to preserve and which ones you want to drop. And currently we employ three predefined strategies for this purpose. The first two are very common, and as you probably know them, for example, from Git, we can simply decide to take the changes from the source side and drop the target changes, or we do it the other way around. Um, a third strategy is called preserve created elements. So if a user decides to add new information, often we want to preserve it. For example, here or as before, we have added a new method and we probably want to preserve this kind of information. So hence the strategy revokes only those deletions that block the new information from being translated, which would here be the deleted document, which is no longer deleted and the deletion is revoked. So besides the conflict resolution, you can further configure also our synchronizer. For example, you can decide whether you want to map new elements onto one another, as you can see on the right, instead of simply translating them each, as you can see on the left. And then changes, for example, such as refactorings from the last slide, only break very small sections of your model or only small parts, which we actually can repair for you. However, if you decide to also retranslate them, of course you can do that. And finally, we can always clear your models so that they are again consistent to your TGG. But if you want to keep some inconsistencies to fix them later, for example, you can of course also configure this. And our approach is implemented in the state-of-the-art graph transformation tool eMoflon, which employs incremental graph pattern matching to find the rule application locations in a way that scales with the number of changes of a model rather than its size. And for our approach, we wanted to find out if you can preserve this property. So we investigated two scenarios for this purpose, where first we fixed the number of concurrent changes to our models and increased the model size steadily. And then second, we fixed the model size and increased the number of changes. And for both scenarios, we measured the initialization time, where we find all matches for the still consistent models. And then we measured the time it takes to apply the deltas, detect conflicts, and restore consistency. And here you can see our first scenario, where we fixed the number of changes to 100, where each change actually inflicts a conflict. We increased the model size to around 1.2 million nodes on both source and target side. And as you can see, the initialization time scales linearly with increasing model size. However, the time it takes to analyze the changes and resolve the conflicts stays constant. In our second scenario, we fixed the number of model elements to around 520,000 and applied up to 2,000 changes, where we have plots where 25, 50, 75 and 100% of these changes actually cause the conflict. And while the initialization time stays constant, as expected, we can see that the conflict resolution time scales linearly with increasing number of changes, and that the kind of change does not have a huge impact to the overall performance, which is exactly what we wanted to achieve. However, note that the results here come from purely synthetic models. Summary. I showed you a novel concurrent synchronization approach that scales with the number of changes rather than the size of the model. At least we can say that for our test suite that we have for eMoflon. At least, or we are able to detect these conflicts without touching or altering the models, which is a huge advantage. And our approach is also able to detect these conflicts in a deterministic way, at least for a given dependency graph. And for the future, we would like to evaluate our approach on a wider range of TGs and scenarios and also incorporate more kinds of conflicts, which currently are only three. So two of them I showed you. However, we are also able to detect attribute conflicts, which I had to omit here due to time reasons. We also want to provide more resolution strategies and finally also offer more ways, for example, via the use of a domain-specific language to give you the opportunity to specify your own custom conflict resolution policies. And with that, I'm at the end of my talk, and I hope you enjoyed it. Thank you very much.